This is example 12-6, depth after sluice gate. So we have our little sluice right here. We have 60 cubic meters per second. That's a fair amount. And it goes under the sluice gate. We get that y1 is equal to 6 meter, and we're asked to find what y2 is and what the type of flow is downstream. Also, what is the maximum volumetric flow that can pass through the gate? All right, to do that, we will start by writing our specific energy equations, right, for y1 and y2. Now for y1, we can say, well, we can just say E, I guess, right? E would have to be equal to E1, so we don't have any bumps or anything like that. And that is, of course, V1 squared over 2G plus Y1. All right, but what's the velocity here? Well, we're going to say if this is far enough upstream, then it's not really moving a whole lot. So we can say equals 0. All right, so that means that is equal to Y1 then. And that has to be equal to E2, right? Because we know the inner specific energy is going to be the same at E1 and E2. And so we can say, with that, we can say, well, that would have to be V2 squared over 2G plus Y2. I'm sorry. You know what? Just let's stick that up there. Let's just erase this real quick. I think we can sneak that in here. Would be V2 squared over 2G plus Y2. Now we're not given the velocity, we're only given the flow rate, so that would be Q over A2 squared divided by 2G plus Y2. That, of course, is then Q squared over 2GA2 squared plus Y2. And that is then Q squared over 2 times G. Doesn't look like a G. Looks like an 8. 2 times G. A is a rectangle, right? This little rectangle right here, where the height of the rectangle is y and the width is b, so we'd have b squared times y2 squared. Right, and that, again, if we go all the way back, we found that that would have to be equal to y1. Right, basically we're taking the location where we only have potential energy and we're turning that into a mix of kinetic energy and potential energy. All right, so now if we look at this equation, right, we're trying to find y2. Q is given, the width is given, drawn in here, 4 meters. Worried there for a second. And y1 is given as well as 6 meters, so the only thing we don't know is y2. So we can solve this for y2. I'm missing a y2. That's why I was looking strange. All right, we forgot to add y2 here. Otherwise, it'll be easy to solve. All right, so if we multiply all this by y2 squared, we'll get q squared over 2 times g times b squared. y2 times y2 squared is y2 to the third power equal to y1 times y2 squared. All right, so we have a cubic equation. Can rewrite that as y2 to the third power minus y1 times y2 squared plus q squared over 2gb squared is equal to 0. And then we can plug in numbers. So that'd be y2 to the third power minus y1 was 6 meters, y2 squared plus flow rate was 60 cubic meters per second squared divided by 2 times G times 4 meter squared is equal to 0. All right, if we plug those numbers in, of course, looks good at the beginning. y2 to the third power minus 6 meters times y2 squared plus 11.46789 meters cubed is equal to 0. Stick that into whatever solver you want to use. So we get y21 is equal to 5.639407762 meters. We get y22 is equal to 1.61766674 meters, and y23 minus 0.479981192 meters. Just like with the other ones, the negative one obviously doesn't work for us. Can't have negative depth. So that means we're left with two results here. In the way that we can interpret these two results, as we go back to our figure, we can say, well, the first one is actually where the flow in this channel is still subcritical. Right, up here it's going to be subcritical, and then it goes through its transformation and becomes supercritical. Right, so we can say, you can say it this way, right? We can say that y, let's call it before, is then going to be deeper one, right? Because it's subcritical, 564 meters, and y after is then the lower one, which was 1.62 meters. All right, so before the gate it's subcritical, after the gate it's supercritical. And then the last thing that we're asked for is the maximum flow so that we can get through this sluice gate. Right, so that would be Q max equal to width times the square root of 8/27 times G times y1 to the third power is equal to 4 meters times 8/27 times 9.81 meters per second squared, and then upstream it was 6 meters deep. Real quick, does this work with our units? We have an S squared that's going to turn into seconds, which is good. And then we have meters to the 4. The square root of that is 2, so that's good too. That all works. Because we're multiplying by the last meter here, so we'll get meters cubed. That gives us 100.227 cubic meters per second, or 3 significant digits, 100 cubic meters per second. Quite the capacity. All right, so this was example 12.6, where we figured out what the flow would be after the sluice gate and what the maximum flow would be that we could get through the sluice gate.